Okay. Just before we get going, to mention a few things. So I was looking at the exams. It's not too bad. I mean, obviously the short answer points aren't in there, so they're all going to look a little bit lower, right? There's still 15 points that can be added in there. I think the average right now was like a 65, 66, but that's obviously missing 15 points. So hopefully, even if we get 65% of those 15 points, that should push the average up to at least a 75, which is usually where I see it, right around kind of mid 70s. So I'll try to work on getting those graded tomorrow and Friday. I'd like to Friday have kind of grades updated with exams included. I'll also kind of be switching some things around in Canvas, so you'll start to see. I'll start weighting the categories by what they're supposed to be weighted by. So up to this point, everything kind of the homeworks are all just kind of 10%. Now we have an exam grade that's weighted a little bit differently. So I'll get kind of that all updated on Canvas once I get those short answer portions graded, which I said hopefully by the end of the week. If not, I might put a little bit of time in it this weekend and try to get it kind of completed this weekend. So I've got all of your guys' Excel 2 graded except for 2 people. I already talked to one. That was having issues with your file. So if I ever have issues with your file, or I think you maybe accidentally uploaded the wrong file because it's blank, I leave a message for you on Canvas, like where I would usually put comments about what points were taken off. If you can resend me the file and just show me a screenshot, a couple of you I've done this before, where it says last date modified. If you open the folder, it should have that date right next to the file, and I can tell you haven't worked on it past the due date. Then I'll accept it and we'll have no problems there. So there's, like I said, there's 2 of you out there, so check Canvas to make sure on that. Also, there is something that slipped. This is my fault, but it'll help benefiting you guys. And if you're worried about the exam grade here somewhere, you can get a couple more points in the class. So I think there was some confusion by some people about those online quizzes and exactly when they're due. So I think the first few I had kind of by the end of the day, as opposed to kind of the start of the next class. So there's a decent number that are late. I feel kind of mean to put a bunch of zeros in there in the grade book. So what I'm going to do, and it kind of stops today, every online quiz that's up there, if you for some reason missed it, you can go back, and by the end of the week, you can kind of go on and do it, and I'll count it for whatever grade you get on it, right? So essentially for these first whatever month of online quizzes, you can go back right now and do them, and I'll count no late, right? I won't just give you zeros if it's late, okay? So I would go back on. If you missed any of those, right? You can't necessarily redo the quiz, right? If you've already done it, it's going to have the points in there. But if you didn't do it, you can go back in and submit it, and I'll count it as though it's not late. From here on out, every online quiz is due prior to the class, right? Not 5 minutes in the class, not a half hour in the class, prior to the class, right? And so from now on, once at the end of this week, every online quiz, if you submit it late, it's just going to show up as a 0, okay? So get on, kind of get some of those points back, do any online quizzes that you missed, and then I'll kind of get the grades updated by the end of the week on that as well. I also posted a Learn Smart, which I want you to read by the end of the day Friday, right? So it'll be some of the stuff we talk about today and Friday, but also have a lot more stuff we're going to talk about next week in there. It's about, I think I have it set, should on average to about 10 to 15 minutes, somewhere in there. Get on, get those easy points, get that done by the end of the day on Friday, okay? I'll also likely post the next Connect homework up there. We'll have not covered enough materials to go through it, but I'll just get it up there early so that as we start going through material, you can start to look at kind of the questions, and the questions will be ordered in terms of how we're going through things in class. So you can start to chip away at that homework as we go, okay? Any questions for me before we kind of jump into some new material here today? Let me see if there's nothing in the chat. Okay. No questions for me on anything? How do we feel about the exam? Not good? I know these exams are tough. I mean, usually this is why I say on the homework assignments, because you can reach out to me, you can kind of get help. Those Learn Smarts, we're doing these online quizzes, those are where you can get some easy points, because I expect the average of the exams to be a little lower. I mean, 75 is not bad, right? But as long as everyone else is doing all the homeworks and everything, typically you can kind of raise your grade up. So the average, hopefully, I mean, sometimes I've seen it, in the B range, right? So yeah, get on any of those online quizzes you missed, learn smart this week, and that should cover it, okay? Like I said, I'll try to get those short answer questions. I'll start trying to get those graded, hopefully by the end of the week. If not, through the weekend, I'll get them completed, okay? All right, so there are no questions. We will jump into things for today. So we left off right before the exam talking about discrete random variables, right? So now we're going to kind of switch, transition to continuous random variables. So, you know, we've talked about continuous variables before. I think I've shown you this slide 2 or 3 times now. All right, it's not just integer values. Now we can see things like 6.3152, right? Any value, if it's truly a continuous random variable, we should be able to see any value, okay? So just like with the discrete random variables, we have these probability, before we call them kind of probability mass functions, but probability density functions, or probability mass function give us a probability density distribution. It's just now we don't have to look at discrete values. We can look at any value. So things are going to play a little bit different. When we're dealing with a continuous random variable, and I'll bring this up now, and we'll talk about it later in the class, the probability of any one value is actually 0. If you think about it, we'll do a nice, let's say we could have any number, but every number is equally as likely. Well, even between the values of 0 and 1, how many possible numbers could we see? An infinite amount, right? If it's truly continuous, we could see an infinite amount of values. Let's say they're all equally as likely. Well, if we had 100 values, we said, what would be the probability of each value? Just 1 over 100, 1 over n. Well, if our n is now infinity, 1 over infinity is actually in the limit 0. So the probability of any one value will be 0. So these probability kind of mass functions, we can actually only find the probability over an interval, right? The probability of any one specific value, like the probability of 6.31 would be 0. But the probability I see this continuous random variable take on a value between 6.5 and 13.9, I can find a probability that I see something over that interval, okay? So we can use a table or graph to show this. We'll have some density function. It'll become a little bit less important than it was with the discrete random variables, but the conditions are all going to be very similar, right? So it has to be, if it's continuous, we don't see any sudden jumps, like this is a nice continuous line, just down here in the corner. A lot of times we deal with this nice normal distribution, right? It's this nice continuous line. We don't see any jumps in it, right? It's a continuous line. For any space we're looking at, any interval we're looking at, if this function is giving us probabilities, they have to be 0 or higher, right? Once again, probabilities, we can't see negative values. And then if we were to add up across the entire range of possible values we could see for x, so if we looked at all the possible outcomes, we think about it, we can almost break this down, right? And if this is my distribution, I think they do this in calculus a lot to try to get the idea, but right, we could almost think about this as a bunch of really tiny rectangles, and all those would represent is the probability of these different intervals, right? Because on my y-axis here, this f of x function is really telling me probabilities, right? And so if I were to add up all these really small rectangles, would be the probability of every possible outcome I could see for x. They should all add up to 1, right? Just like when we were dealing with discrete random variables, we took every possible outcome, added up all the probabilities that had to add up to 1, right? That's the entire experimental outcome space. It's just now, instead of the entire experimental outcome space being like a box, right? We used to think about it that way with the Venn diagrams. Now, our entire experimental outcome space is just this area under the curve, okay? So we kind of switch things visually a little bit, but we're still thinking about, here's all my probabilities, right? All these little rectangles. If I added all those up, they should add up to 1, which, if we write this out, technically, adding them all up, you can think about we'd be integrating that function across every outcome. We're not going to be doing calculus here, but if that makes sense, because you've seen on the math, you take on the math courses, that's really what we're doing, right? If we're looking at integrating over that function over the entire experimental outcome space, all the values of x we could see, it's really just adding up all those probabilities. So they should be kind of an area of 1 under that curve, okay? So very similar to what we're doing with discrete random variables. You know, I drew this up on the board just now. Typically, we think about a normal distribution. Today, we'll talk about a continuous distribution, but after that, we're basically going to be dealing with just the normal distribution for the rest of class, or for the rest of this course, okay? So we should get used to kind of seeing this distribution. So the area under this curve is 1, right? I've already kind of talked about that. We can also think about, and this will become a little more apparent once we start dealing with the normal distribution, but we could also have a cumulative density function, right? So once again, cumulative meaning, what's the probability I see this value for x or anything below it, right? And so now I'm starting to think, okay, I'm getting the probability of an interval, right? I said we can't get the probability of any one specific value, but a cumulative density function would give me the probability I see x or anything below it, right? So, you know, we could write this as capital F of x. It's not the probability kind of density function, it's a cumulative density function. As this cumulative density function, as x gets higher, right? So as x gets higher, the probability I see something that's x or lower is getting closer and closer to 1. As I think about values that are small for x, well, this area is not going to be very large, or it's getting closer and closer to 0. So that's all we're saying here. For very large values of x, that cumulative density function is getting closer and closer to 1. As we have really small values for x, the area to the left will be very small or closer and closer to 0 as we look at smaller and smaller x values. Okay? Let me just double check no one's waiting here because I saw a couple people getting wait. So, I kind of give a cruddy visual here, but just as I was talking, but you can kind of think about, what if I wanted the probability x is less than or equal to a? That would be that cumulative density function. So think about where is a, what's the area to the left of it, but under this curve, right? That'd be like adding up all these probabilities up to the value of a. Well, that's just our cumulative density function. If we were to plug in that value of a, it would give us the probability we see a value for x that's less than or equal to a. Okay? What if I wanted the probability x is greater than or equal to b? Well, I've got b over here. I want the probability x is greater than or equal to b. Well, my cumulative density function doesn't give me the area to the right of b. It looks at what's the probability I see b or anything below it. So what's something that we were doing even with the discrete random variables or even way before that we could use here? Well, if this is event A, how could I find A? I can also look at it as 1 minus the complement. Well, what's the complement here? If I can get my mouse to work. What's the complement? Well, that's just that it's less than B. Well, that's what my cumulative density function does. If I plug B in there, it gives me the probability of B or anything below it. Now, one nice thing about these continuous random variables, the equalities don't matter as much. It really mattered with discrete random variables, right? If I say less than 3 or less than or equal to 3, I had to include another outcome. Well, here, if I think about what's the probability x is less than b, it's kind of trippy, but the probability that x is less than b is actually the same as the probability x is less than or equal to, because I'm only including one more value, right? When I say, we'll think about it this way. When I'm saying, excuse me, if I want the probability x is less than 10, well, what's the first, I can kind of think about, it's actually going from 9.999 repeated all the way down to whatever the lowest value is. But if I say the probability that x is less than or equal to 10, I can actually rewrite that as, well, that's actually just the probability x is equal to 10 plus the probability x is less than 10. But what's the probability of any one value? 0. So these actually end up being the same thing. So the equalities don't matter as much for us here. It kind of makes life a little bit easier. And we don't have to know that for sure, but I'm just kind of trying to give you a rationale behind why. Okay, what's the probability of being between two values? Well, now I'm thinking about visually, I've got these two cutoff values from an interval. It's just the area in between them, but under the curve. I could shade this area in. Well, if I think about how could I find this area using my cumulative density function? Well, if I plug A into that cumulative density function, it would give me the area to the left of A. If I plug B into my cumulative density function, it tells me the area to the left of B. So if I have those two things, right, I could just subtract the area to the left of A from the area to the left of B, and it would give me the area that's in between, right? Or, I'll kind of give you another way to think about this. Just kind of drawing out, I think sometimes maybe this helps. So here's A, here's B. Here's the area to the left of A. If I subtract that from the area to the left of B, like I'm taking this out, all I'm left with is what's in between them, right? So kind of because they overlap, and I subtract it out, I'm just getting rid of that tail from the probability of B. Okay? Does that kind of make sense? Any questions on that? And we can write this out formally using that cumulative density function. We probably won't actually write this out formally a lot, but we'll be using this idea that I want the probability being in between two values. I find the probability of being less than the lower value, the probability of being less than the higher value, and subtract out that probability of being less than the lower value from the large value, and I've got what's in between, okay? All right, and I'm gonna kind of go through this one quickly. We'll kind of revisit this once we get to the normal distribution, but, right, if I wanted the probability of being outside of that range, well, I could have taken this and subtracted it from 1, right? Because the area under that curve is 1, so if I have this blue area, if I subtract this blue area from 1, I'm just left with what's in the tails here. So we could find the probability that we're in between, subtract it from 1, and we have the area in the tails. Okay? Like I said, we'll revisit this once we get to the continuous distribution. Probably next class. I probably won't start it today. So probably on Friday, we'll revisit a lot of this. But I'm just kind of setting up so we can start to think about what we're going to be doing with these continuous random variables. Okay? All right. So just like with the discrete random variables, we have some very specific continuous random variables we can talk about. The first one we'll talk about is the uniform. Okay? So the uniform distribution, kind of the, I guess, definition of what makes a uniform distribution is that any equally sized interval has the same likelihood of occurring, or the same probability of occurring. So if I think about what's the probability this variable x is between 3.5 and 4.5, that would be the same probability as seeing it be between 11.5 and 12.5. Two equally sized intervals, they're actually here, they're intervals of 1, they would have the exact same probability of occurring. So I want to think about what this starts to look like. Remember, my y-axis is kind of representing my probabilities, kind of representing probabilities. That's probably the easiest way to think about that. So I look at every possible value for x. The probability I see it between, well, I don't remember if I use these values, but 4.5 and 5.5, that's going to have some probability of occurring. The probability I see it be between 6.5 and 7.5, equally sized intervals of 1, same likelihood of occurring. So anytime I look at these intervals of 1, I'm going to have the exact same probability, and so I end up with not a nice normal distribution, but I have this kind of flat box of a distribution. And where does it start and where does it stop? Well, whatever my minimum and maximum values are, right? So if this is something like, we could be doing interest rates, right? And if I have them written down in decimal form, I could see any value for the interest rate. Let's just assume for a second they're equally as likely, but I know they would start at 0 and stop at 1, right? Or, we'll look through some other examples and kind of see we'd have these different min-maxes, but yeah, in that example I gave, we can think of some variables that have a min-max of 1. All right, so what's going to end up being true is, where does that line go? So I drew that straight line, right? But what is that value for y, right? What is that value for this density function? Well, I'm going to write the minimum and the maximum here as C and D, right? So I can think about my minimum is C, my maximum is D. And hopefully once we get to kind of completing these, that'll make a little more sense why we're kind of just notating them that way. But if you wanted to right now, write this down. D is the maximum, C is the minimum, so 1 over max minus the min. And this kind of intuitively makes sense. Think about it this way, even though it's a continuous random variable, if I say looked at the values between 0 and 10, how many intervals of size 1 would there be between 0 and 10? So if I looked at an interval of 1, how many of those would fit between 0 and 10? Let's assume I have 0 and 10 here. The first interval would be 0 to 1. The next one would be 1 to 2. How many of those would fit? My maximum is 10. I would have 10 equally sized intervals of 1. What would be the probability that I was in any one of those 10 intervals? 1 over 10. There's 10 intervals, they're all equally as likely. So what this is saying is we aren't breaking up intervals into 1. We could look at intervals of any size, right? So if I instead broke this down to 100 intervals of 0 to 10, right? I would have 100 equally sized intervals, but they wouldn't have the probability of 1 over 10 of occurring. They'd have the probability of 1 over 100 of occurring. Well, I can break this down into whatever I want. I could break this down into like a very infinitesimally small interval. So how do I find the probability of any interval size? Well, I'm actually thinking about that range of 1 over the maximum minus the minimum. So we think about it this way. I'm going from 0 to 10. If I had 10 equally sized intervals, it was 1 over 10. I wanted to break that down from 0 to 10 into 100 equally sized intervals. Well, I still had 1 over 10 here, but now in order for me to have a probability space of 1, I'd have to multiply that by, if I was using 100, 100 times 1 over 10 would only give me a probability of well, I think I'm going to confuse you here. So for right now, let's just assume that we know the height of this distribution is 1 over the maximum minus the minimum. Once we actually start dealing with intervals, I'll come back and revisit this discussion. But 1 over the maximum minus the minimum. Okay? I think the best way to think about it is if we did break it down into intervals of 1, how many would be within there? From 0 to 10, there would be 10. From 0 to 100, there would be 100, so on and so forth. So we've got this uniform distribution. Just like with the normal, the area under the curve is 1. Now our curve's a little weird because it's a flat line. It has a beginning and ending, but this area under the curve and between our minimum and maximum has to be 1. Right? So the area under the curve is 1, and the height of this distribution will be 1 over whatever our range is, right? 1 over the maximum minus the minimum. And then here, this is just to be a little bit formally correct. If I'm outside of that range, right? If I'm outside of the minimum or the maximum, the probabilities are just 0. Right? So that's all that's saying right here. Okay? All right, so if I wanted the probability of being between two values, say A and B, I can actually use this density function. Okay? Now, where does this come from? I'll show you what I think is an easier way to think about how to find the probability of any interval. So let's go back to this. And I'll use 0 to 10 again, just because it kind of keeps our numbers nice and easy for right now. So we know the area under this curve is 1. Right? We know the height is going to be what? 1 over 10 minus 0, or 1 over 10. Okay. So what if I wanted the probability, and B, we say that is the maximum of our interval, A is the minimum of our interval. Remember, we said the minimum and maximum of the distribution we could call C and D. Well, let's say I had, my interval was from 4 to 5. Well, this is the area I want between 4 and 5, but under the curve. But that's just a rectangle. How do I find the area of a rectangle? I just take the length times the width, or base times height, however you want to say it. Right. So what's the length of my interval here? It goes from 4 to 5. So the length of my interval is 1. We'll write this out not using the numbers. That's actually the length of my interval is b minus a. Right? Take where my interval ends, subtract where it begins, that's the length of my interval. What's kind of the height of this rectangle? Well, that's just the height of my distribution. So 1/10. Right? Or if I wanted to write this out using C and D, I'd be multiplying that by 1 over d minus c. Well, if I multiply by 1 over something, it's the same as dividing by it, which is where this comes from, right? B minus A over D minus C, right? But if you don't want to use this, I honestly think find the height of your distribution. So here we had it was 1/10. Just multiply that by whatever your interval length is. If my interval length is 1, the probability I see it within there will be what? 1 times 1/10, so 1/10. If my interval was, let's say my interval was, so let's say I was going from 4 to 4.1. Well, now my interval length is 0.1. Multiply that by 1/10. Now my probability would be not 1/10, but 1/100. Right? I could find any interval that I'm interested in now. Okay? So this is the equation that we're going to use to do that. Or draw out the visual and just think about finding the area of a rectangle. That's how I would do it. I think it's the easiest way. Okay? We'll go through some problems with some actual values here. So yeah, I kind of had this up on the board, but whoops. All right, the area in this curve is 1. Oh, before we get to some problems, we'll also talk about we could find the mean and the variance of this variable as well. So just like with discrete random variables, sometimes, you know, if we're dealing with a very specific continuous random variable, it has its own equation to find the mean and its own equation to find the variance. So what ends up being true is if everything's equally as likely, right, we're really just finding the middle value of that uniform distribution. That's our mean or our expected value. So if it starts at 0, stops at 10, what's the middle value there? 5. How did I get that? Well, I just actually found the average between my minimum and my maximum. If instead my minimum was 10, my maximum is 20, well, what's the middle value there? It's kind of easy to think about. It's 15. Well, what'd you do? 20 plus 10 divided by 2. So to find the mean or expected value, it's as easy as add up the min and the maximum, divide by 2, or just find the average of your minimum and maximum. Now the equation we have for the variance, not as intuitive. You can look at the mathematical proof, but what ends up being true about a uniform distribution is that the variance will always be whatever the range is squared divided by 12. Right? Where does that 12 come from? You can look through the mathematical proof and you kind of see, well, here's the mean, it's divided by 2. We're taking deviations from that square. So you can kind of imagine eventually we get to, the math works out to this is 12. And this kind of makes sense. If my range of my uniform distribution is wider, right? So let's say I'm going from 0 to 100. Well, I'm going to see a lot more variation in the outcomes for that variable than if it only went from 0 to 10. So my variance is directly related to the range of values that I could see. Okay? And then, of course, the standard deviation, we could just take the square root, right? That's the same as everything else we've done in the past. Okay? So let's say we have this example. We have this movie coming out, Santa with Muscles 2, right? We're thinking about, there's going to be popcorn demand at the movie theater, although this example I might have to kind of nix after this year. I think it may no longer make much sense. But let's say demand for popcorn while this movie is going to be played goes from 1 to 10 pounds. Okay? So what would the mean of popcorn demanded be? Well, now I'm not going from 0 to 10 like the other examples. I'm going from 1 to 10. So I'm looking for the middle value of my uniform distribution. That's as easy as add up my maximum and my minimum, divide by 2, or just find the mean between my minimum and my maximum. Add them up, find the average, right? So here, 10 plus 1 divided by 2 gives me that mean of 5.5, right? That one shouldn't be too bad. I think finding the mean for these is pretty straightforward, kind of intuitive. Now, I will say one thing you have to be careful with is if you're dealing with negative values, Doesn't make sense in the context of this example, but let's say I had a uniform that could go from -10 to 10. Intuitively there, you know the mean or the middle value would be 0, right? But if I, for some reason, like took 10 and try to subtract -10, I would have 10 plus 10, which is 20 divided by 2, which is 10. Well, that's not the mean, that's the math. So no, be careful with that negative value. And instead of adding, you accidentally subtract, you could end up with some weird values there. But even if it's negative, you just simply add these two values up, divide by 2, and that will give you your mean. Okay? Let me make sure we don't have any questions here. And then this is an actual movie, Santa with Muscles. If you guys like terrible 80s, early 90s movies, this one's a great one. It's with Hulk Hogan, but I would suggest probably passing on it, but it is kind of funny because it's so bad. So anyways, we could think about what's going to be the height for this distribution for our example. Well, our maximum is 10, our minimum is 1. So what should the height for our distribution be? The height is just 1 over maximum minus the minimum. So in this example, what would the height of our distribution be? I think someone said it. Just 1 over. What's the maximum minus the minimum here? 10 minus 1 is 9. I said the height of the distribution is 1 over the maximum minus the minimum, so just 1/9, right? It's as easy as that. So I've got this drawn out now, and I'll kind of make this full screen for the video here in a second. But what if I want to find the probability I'm between B and A? Any two values. Well, I'll simply take that height, which I now know is 1/9, multiply it by whatever the length of my interval is. How do I find the length of that interval? Well, it's just the difference between A and B. Right? So let's put some actual values to this. So what is the probability, the same example, that the movie theater, if they made 9.5 pounds, what's the probability that demand is too high and they didn't make enough? So visually what we're thinking about there is what's the probability that if they make 9.5, it's not enough, which the only way that's not enough is if demand is greater than 9.5. When we say greater than 9.5, it's not like with our discrete variables like the Poisson, we're like, where do you stop? We know where we stop, right? We have to stop at the maximum. So we want this area, so the length of our interval, it goes from 9.5 to 10. So what, 10 minus 9.5 is 0.5, right? So you would just take 0.5, multiply it by the height, which is 1/9. That ends up being 1/18, which I can't remember what that is off the top of my head, but right? All you did there, you could have also plugged it into the more formal equation instead of thinking about it as the area of a rectangle. You could have plugged in your interval length, 10 minus 9.5, in the denominator, plug in your maximum minimum, and you get that, what, 1/18, right? 1/2 times 1/9, or 0.5 times 1/9, will give you that 1/18 or 0.056. Now, like I said, you can use this equation every single time. I think it's way easier to think about what the length or height and length or width and length, whatever you want to call these of your rectangle are, right? You always know the height, and you can just get the width of that interval by the difference between your B and A, wherever your interval starts and stops, okay? Any questions on that before we keep moving? We're okay with that? So what if I asked you, what's the probability that the amount of popcorn demand is between 3.25 and 3.75? What should that probability be? You can answer really quickly. What's the length of that interval? 3.25 to 3.75, the length of the interval would be 0.5. What was the length of this interval? 10 and 9.5, it was also 0.5. We said for the uniform distribution, equally sized intervals are equally as likely. So the probability I see demand be from 3.25 to 3.75 would just be that same 0.056, right? And you could plug the numbers in, right? Instead of 10 and 5 now, my interval is 3.75 and 3.25. Math works out to be the exact same probability, right? So equally sized intervals have the same probability of occurring. So we're getting time. Okay, I'll do another one here because I know that I didn't include it. So let's say we're dealing with the same exact thing, but instead I ask you, oops, what's the probability it's between 4 and 4.5 or between 7 and 7.5? Right? Using the information that we just had, why should this be pretty easy to find? Well, what's the interval length here? 4 to 4.5, the interval length is 0.5, which we know the probability that an interval of 0.5 occurs is 0.056, okay? So we know that this area is 0.056, which also means if this is going from 7 to 7.5, interval length of 0.5, this area is also 0.056, right? So if I want the probability I see it demand be between here or within this range, all I do is add those two areas up, right? And why this makes sense, floating around in the background, if we want the union of two events, right, do I see the variable take on values in this range or in this range? The reason why we can simply add those probabilities up is I don't have an intersection there, right? As long as what I'm thinking about, the intervals I'm thinking about don't overlap, I can simply add up the probabilities because they're mutually exclusive. There is no value for demand that's in the range of 4.5 and 7 and 7.5, right? There's no number that those two would be, involved in. Now, I don't get crazy like this, but you can start to imagine, what if I asked the probability of being like between 4 and 6 or 5 and 7? Well, now we do have two rectangles, but they overlap. We'd have to think about their intersection. Not going to necessarily push it that far in these examples, but if we wanted to push it further, like outside this class, we could, right? But the most I would ever ask is like, what's the probability I'm in either one of these two intervals that don't overlap? And then it's simply find the probability of each interval, add them up. And if they're the same length interval, well, it's really easy. I only have to find one. I know the other is the exact same. Okay? So in that one would be what? 0.056 plus 0.056. So what? 0.112. Right? Any questions on that one? I know this is kind of not in the slides, and I kind of just did that on the fly. I know we're going to have a little extra time here, so I wanted to make sure I went through that. Okay, all right with that? So what if I have the same example, but now I say, okay, they made 9.5 pounds. What's the probability that they made exactly the right amount, that demands exactly 9.5? Based off what I said earlier, what should this probability be? The probability that we see this continuous random variable take on exactly the value of 9.5 should be 0. Between 1 and 10, we technically have an infinite number of possible values we could see, right? And we said if they're all equally as likely, then the probability we see it 1 over infinity, well, that's in the limit 0. Now I can prove this if we actually just treat this like we were treating the other example. If I want the probability of exactly 9.5, where does my interval start and stop? Yeah, right? It starts and stops at 9.5. So my values for A and B would be 9.5, 9.5. If I plug those in my density function, or think about what's the width of my interval there, it's just 0. And 0 divided by anything, or 0 multiplied by anything, if you're multiplying by the height, instead of using this density function format, it's always going to be 0. So that's kind of helps, I guess, support what I was saying earlier, so you don't just have to take my word for it. But here we have a nice example where we can prove that to ourselves. Okay? 10 minutes. We'll kind of start. This story is kind of interesting, but maybe I'll start next class with it. It doesn't have a whole lot to do. This is just a little story about the guy who kind of came up with this normal distribution. So we had a very specific continuous random variable, which was the uniform. The next one we're going to talk about is the normal distribution, or sometimes called the Gaussian distribution. Right? So I might start off next class just to kind of make it a little more interesting with a story about him. I don't know, really, really smart guy. Figured out like there's all these things in nature that all seem to follow this same type of distribution. A lot of biological things. So if we look at like human height, human weight, as long as we kind of divide that by gender there. IQ looks like it follows a real nice normal distribution. Rainfall, temperatures, you know, as long as we're looking at the same location. So look at a bunch of these different stuff. We see the normal distribution pop up everywhere, right? So he kind of came up with this. So we sometimes call it the normal or the Gaussian distribution. So I'll skip this little story about him. And the normal distribution is kind of also referred to as the bell curve, right? So this nice kind of bell-shaped looking distribution. Got what? Human height, rainfall. He wrote this book about all these, you know, all of these different things that we see pop up in nature that follow this normal distribution. So I'm going to show you this. And we're not going to use this function at all. So I'm just bringing it up to introduce the idea for next class. There is a probability density function for the normal distribution. It is not as easy as 1 over the height and then you multiply by the interval length. It would look something like this, right? So you know that this function gives us that nice bell-shaped curve, right? If I were to plug in a bunch of different values for x, I would have this nice shaped curve. And then I could integrate over that function from, you know, whatever, you know, wherever it starts. I don't know, let's say it starts at 0, all the way to a. I could find the probability underneath that curve, but in between those two values. I'm not going to make you do that derivation. I'm not going to make or do that integration. We actually have a table for this, which is up on Canvas, just kind of floating on here, called the Z tables or standard normal tables. We'll actually start looking at that table next class. So I don't know if you're watching kind of the Zoom lecture or you're attending, what I would do, if you can pull it up on your computer or whatever, that's fine. But to follow along with what I'm doing, it's probably helpful if you can somehow get that printed out, right, and bring it with you to class or have it sitting next to you as you're watching the Zoom or even the YouTube, to be able to follow along with what I'm doing on that. Because show you right now, I mean, I'll zoom in on it to make it easier to see, but I have to actually download this. I can rotate it. But you know, these numbers are kind of small. I can only make it so big, and then when I make it bigger, you can't see the row and column headings. And so I think it's probably easier to just have it in front of you. So that would be my suggestion. Try to get that printed out and get a copy of it. It's up there on Canvas, so do that maybe kind of before next class, or for sure next week. I think it would be a lot more helpful to have that in front of you. Okay? All right. So anyways, you can kind of see some of the things that are in this function. We have this natural this kind of crazy weird number pi that ends up floating around in the normal distribution. We've got the mean, we've got the variance, we've got this natural number e that ends up being there as well. So, you know, you could probably watch, I'm sure there's like YouTube videos of people who have maybe participated in certain recreational activities that will like talk about pi and e in the normal distribution and how wild and crazy this is. And I don't know, probably introduce the idea of aliens in there, you know, these, I don't know, you know, just like geeks and nerds that are kind of want to geek out about this stuff. But it is kind of interesting these both pop up in that probability density function. But really what this normal distribution is dictated by is, well, what's my mean and variance? Because I can have a normal distribution for height, but for men it's going to look very different than it will for women. It's still a normal distribution, but we would know that for women that normal distribution would probably be shifted to the left, right? It has a different mean. So you can have normal distributions for tons of different variables, but that normal distribution, yes, it's a bell-shaped curve, but where it will be plotted at, like if we have x here on the x-axis, well, the mean, we kind of shift that normal distribution. And we'll also talk about next class more in depth, how high or kind of flat that distribution is will be dictated by the variance, right? If I had a really high variance, I know that I'm going to see values further from the mean. I know if I have really low variance, I'm going to see more likely I'll see values around the mean. So kind of the height of our distribution for the normal distribution will be dictated by the variance of whatever variable we're looking at. And then kind of where it's at along the x-axis will be shifted by whatever the mean is for that normally distributed variable. Okay? So we won't ever actually have to use this function, but it'll be always floating around in the background. Okay? So, you know, some of the properties, it's this nice symmetric distribution. So if I'm thinking about this here, if I were to like split this right down the middle, it's symmetric, it folds on top of itself. A nice property of that is the mean will be equal to the median, which will be equal to the mode. We kind of looked at this earlier in the semester. And I mentioned it's defined by whatever the mean and variance are. So we can see normal distributions for height, for rainfall, but they'll have very different means and variances. I think, where are we at on time here? I think I'll save this from next class. I'll give you some more visuals of how the mean and the variance dictate that normal distribution. We'll start to work with that standard normal table to find, okay, if I know what the mean and the variance of this variable are, what's the probability that I see a value below, and here you almost think about it as, right? If I have this nice normal distribution, if I know the mean and the variance, I can start to find the probability that it's less than a certain value by doing some conversion and using those standard normal tables, right? So I call it the Z table there. You might also see it referred to as the standard normal table, okay? All right. Any questions about anything related to the class before we kind of get out of here? Otherwise, I'll work on getting those short answers graded and getting grades updated on Canvas, and I will see you on Friday.